So graphing the equation e to the x plus x over x, we're first going to look at the denominator for the vertical asymptote. So the denominator can't equal to 0, so x can't equal to 0, so we're going to end up with a vertical asymptote through the 0 here. So the y-axis is a vertical asymptote. Looking at the numerator, where the numerator is equal to 0 is where we're going to get our zeros, where it crosses the x-axis. Now, this e to the x plus x, we cannot solve this algebraically. So we could maybe guess and test to get a reasonable approximation. But I've given you the value of x equals 0.57. So this, again, cannot be solved algebraically to get that value. We'd have to kind of guess and test at that. So I'm going to put that in. So at negative, that's going to be at negative 0.57. So negative 0.57, we have y equals 0. So I'm going to put that in probably right about there. As we look at our horizontal asymptotes, we look at endpoint behavior. So as x goes to negative infinity, it's going to tend towards 1. And the reason why that happens is because we end up with this term, e to the negative infinity, tends towards this 0 here. Okay, so we end up with x over x, which tends towards y equals 1. So I'm going to have, as we go to the left, we're going to have a horizontal asymptote at y equals 1. Looking to the right, as x goes to positive infinity, we end up with an exponential function over a linear function. So we have strong over weak. So it's going to essentially just kind of go off to infinity as it goes to the right. So we can then look for our turning points by looking at the derivative. So we're going to differentiate this function. We're going to use the quotient rule. So we end up with e to the x plus 1 times the denominator x minus e to the x plus x, and that times the denominator, which is 1. Squaring the denominator, this is our derivative. Okay, so we can simplify this. We end up with x e to the x plus x minus e to the x minus x. So those x's cancel out. So we end up with just factored form of this. I'm going to factor that e to the x out. So I end up with e to the x minus 1 all over x squared. Okay, so once we have our derivative here, we can see we have zeros. We have an undefined value at 0. And at x equals 1, we have a 0 slope in here. So then we should test some of our derivative values here. So when x is negative 1, e to the x is always positive. The x minus 1 is going to give us negative, and x squared is positive. In fact, only the x minus 1 is going to give us determine positive or negative. So we end up with negative slope through here. Okay, so it's likely going to kind of go through here, go through our 0, and down. Okay, so that's what we're anticipating it looking like. We're going to test our slope between 0 and 1, so f prime at 0.5, plug 0.5 in there. Again, only the bracketed term determines the positive and negativity of that derivative, so it's going down. Looks like a local min. And then we'll test the derivative at x equals 2, and that's going to give us a positive slope through here. So that looks like a local min. So I'm going to plug in my y value, or sorry, my x value at 1, and then plugging into my equation, I get e to the 1 plus 1, so it's going to be e plus 1 divided by 1. And that's approximately 3.72. So drawing that point in at x equals 1, y equals 3.72, maybe somewhere around here. Okay, that's the local min. So it looks like we're going to go down and up through here, and it's going to come through here. Okay, so we should just get the second derivative, although this question did not ask for the second derivative. we should check to see if there's any concavity points here. So doing a second derivative through here. Okay, so second derivative, we're going to differentiate that term again. So this is our second derivative. So I end up with product rule, e to the x times x minus 1 plus e to the x times the derivative of 1 x minus 1, so it's just going to be e to the x, times by the denominator, then minus, we're going to end up with the numerator e to the x, x minus 1, times the derivative of the denominator, which is 2x, and this is all over x squared squared. So there we go. I'm going to go come down here a little bit. So working out the numerator, x e to the x minus e to the x plus e to the x. Okay, sorry, it's just going to need to move this again. Just getting it out of the way. Okay, and then this is all multiplied by, that's a square bracket, so that's multiplied by x squared, and we end up with minus 2x squared e to the x plus 2x e to the x, and that's all over x to the power 4. Okay, so expanding that square bracket out, we end up with x cubed. These cancel out, so we end up with x cubed e to the x minus 2x squared e to the x plus 2x e to the x, and then we can cancel those common x terms and factor out the e to the x. So this becomes e to the x bracket x squared minus 2x plus 2, and then that extra x cancels with the denominator, so we end up with x cubed. Okay, so there's my second derivative. I have at 0, I have an undefined second derivative, so I can test my concavity. Sorry, I should check for the zeros. So I'm going to test where this quadratic factor equals 0, but I'm just going to test the discriminant. So b squared minus 4ac. If I try solving this, I end up with negative 2 squared, so 4 minus 4 times a times c, and I end up with negative discriminant. Okay, so that means that there's no solution. There's no solution for that quadratic. So this quadratic has no solution. So the only place where we can change concavity would be across that asymptote. So then I'll just test my concavity. So f double prime, if we have a negative 1, for example, if I plug negative 1 into there, I'm going to end up with a negative in the denominator. I'm going to end up with 1 plus 2 plus 2, so that's going to be positive. So that's going to give us negative concavity on this side. So it's going to be concave down. And the second derivative, when x is 1, I'm going to end up with e to the x is always positive. I end up with 1 minus 2 plus 2, so that's going to be positive. And in the denominator, it's still positive. So I have positive concavity on this side. Okay, and then that should really confirm what we already kind of knew. This graph was going to be sloping down with negative concavity going through the 0, following the asymptote through here. It's going to follow the asymptote down to the min point, and then it's going to go off to infinity since there's no limit as we go to the right. Our turning point, we only had one turning point here, which is at x equals 1. The second derivative didn't really tell us anything. In fact, this question never really asked for the second derivative, but we can use the second derivative to find changes in concavity. And although we do have a change in concavity, that really wasn't necessary information to draw this graph because we already can see that there's a change in concavity just based on the slope chart.